Welcome back. Today we are going to dive into chapter 8. This is our last chapter of this very short semester. We are definitely coming to an end quick, but we still gotta cover this last chapter, and we're gonna be talking about confidence interval estimation. So at the end of this chapter, you should feel comfortable constructing and interpreting confidence interval estimates for the mean and the proportion. You should be able to determine the sample size necessary to develop a confidence interval for the mean or for the proportion. So you should be able to build them and be able to tell if you have enough sample size to do those interval estimates. So today we're going to be talking about the intervals for the population. So uh, we're going to be talking about when we know the standard deviation and when we don't know the standard deviation. We're also going to be able to build confidence interval for the population proportion. And finally, we're going to finish talking about the required sample size to make sure those confidence intervals are good. All right, with that said, let's dive right into it. So let's say that you are getting ready to finish the semester like we are, and then you're trying to figure out what kind of score you should get on the final exam in order to get an A in the class. And so you send me an email, say, teacher, what is the average for the final exam? And I reply to you is 80. In the past, classes that I taught, the mean score or the average score for the final exam is 80. Well, that kind of gives you an idea. Right now, you say, well, maybe it is a hard exam, or maybe it is the end of the semester, and few people don't take the exam, so that kind of draws down the mean because now it's the data is skewed. So really, well, give you a point to get started to kind of figure it out whether you can get 80 points or not. Uh, it's kind of vague, but if you were to say, you know what, that if I were to reply, well, I can tell you with the 95% of my students scored between 70 and 90%. So now you have a better idea of where most of the data is going to be, or like where most of the students fall for the score on the exam. So when we talk about point estimates, right, we can do estimate population parameter mean with a sample statistic of x bar, or we can do the proportion with pi and p. Anyway, how much uncertainty is associated with a point estimate of a population parameter? So again, how much uncertainty is on that 80%? Yeah, it is the average, but I mean, are you an average student? Are you below average? How hard is the test? It really doesn't tell you much, right? So an interval estimate will provide you more information about the characteristic that does a point estimate. So if I tell you the average score on the final exam is 80, uh, gives you an idea. But again, if I tell you 95% of the students score between 70 and 90, now you can probably feel more confident that you can be on the 90s. So such interval estimates are called confidence intervals. So I can tell you, confidence interval, 95% confident interval that, this is where this is where the data falls. So an interval gives you a range of values. Is going to take into consideration variation in sample statistics from sample to sample. So let's say that you are trying to find out what the final or what the average score is for the final exam for all of the college, right? There is going to be a lot of data. So you're just going to take some samples because you might not have access to all of the data. Not all the teachers might be willing to share that information, whatever. So you are going to take a sample. But from sample to sample, you're going to have variation on what the data is. So based on observation from one sample, that's where we're gonna do our confidence interval. You're not gonna do several samples, you take one sample, right? And that'll give us information about how closeness to unknown population parameters. So it'll give us, taking a sample, it'll tell us how close we are to the population actual mean for the final exam. Normally, you're gonna do 95, 99. 95 is very common. You might do 99, 98, sometimes 90. I mean, you can do any number, and but the most common numbers are 95 and 99. it says in here it can never be 100% confident. Yes, you could be at 100% confident, but it's useless. So going back to my example where you asked me, hey, uh, what the score, what the mean is, and I said, well, I can tell you with 100% confidence that all of my students fall between 0 and 100. I mean, it doesn't really tell you anything, right? It's just useless. That's why it says it can never be at 100% confident, because to be 100% confident is useless. But if I tell you with 95% confidence, it's going to be between 70 and 90, that'll give you a really good range. Or I can tell you with 99% confident, it is going to be between 60 and 100. Now I got in my data is wider, but my confidence also is bigger. Okay, so here is an example, right? On this case, we have a population mean of 368, a standard deviation of 15, and you take a sample size of N25, and we're gonna go over this formula later, breaking it down, but this is how you will get, this is how you calculate that, right? In this case, you, after solving this part of the equation, you will get that 356 is less or equal to the mean, which is 368, which is less or equal to 368.18. So the interval based on this example makes a correct statement about mu, or the mean for the population. So what about other intervals from other possible sample of size 25? And here it is, right? So let's say here's the first sample, here is your mean for the sample. So based on that, if you go back to the formula, you get your lower and your upper limit, and this will contain mu. Here is a second example, right? Again, this will contain mu, but look at this one, number 3 here, right? Your mean is 360 for that particular sample. So your lower and upper limit is going to be outside of the mu. Here is our mu is 368. So in this case, right, it does not contain the mean for the population, and this is what the 5% comes from. So in this case, you have 4 out of the 5 examples contain the mean for the population, but there is one that does not, and that is the one that that 5% that is that is on the alpha, that there is a 5% that it could not contain the mean. Now, in reality, you only take one sample size, right? You're not going to go and take several samples. You just take one, and you just lump it all together. Also, you do not know the mean of the population, because if you know the mean, in practice, you really don't know the mean of the population, because if you knew, then there is no need to do all of this, right? But you do know that 95% of the intervals formed on this manner will contain mu. So you take, you can say, you know what, yes, I only take one sample, but I'm 95 confident that this sample contains the mean for the population. Based on that one sample you actually select, you can be 95% confident your interval will contain mu. That is the 95% confidence interval. Again, if you go to the C table, you can see 95% confidence is based on the fact that C is going to equal to 1.96, and we'll go into more details on that shortly. So this is how the estimation process works, right? Here is your population, right? All of the students taking the final exam. You don't know, again, you don't know what the mean is, right? Mean is unknown. So what you do is you take a sample. So you ask a couple of students as they're leaving their campus, you say, you know what was your score on the final exam? So you grab the sample, and the sample has a mean of 50, right? This is just a random sample of the students that you take, and then so you can see the mean for that sample is 50, and you can say, well, I'm 95% confident that the mean for the final exam at the college is going to be between 40 and 60. So here is the general formula for doing the confidence interval. You have your point estimate, which is the first part over here. This is where you get your mean or your average, and then you're gonna add or subtract the critical value times the standard error. So the critical value is a table, right? Value based on the sampling distribution of the point estimate and the desired confidence level. So you figure out you want to be at 99% confident. or you want to be a 95% confident, or you want to be 80% confident. Remember, the higher confidence level you're going to get, the wider the gap is going to be, right? Again, going back to the example, I can tell you I'm 95% confident that the score for the final exam is going to be between 70 and 90. But if I want to be 99% confident, I'm going to have to make that wider. So I'm going to have to go from 60 to 98. So you might have to extend that. And again, a standard error basically is the standard deviation of the point estimate. So what is the confidence level? Confidence, the interval will contain the unknown population parameter, a percentage, remember less than 100, you can do 100, but it will be useless. So that will be your confidence level, the interval that will contain the unknown population parameter, and then the percentage that you want to be, 99, 98, 95, or any other number. Here you have, let's say you want to do a confidence level of 95%, and on this case you can write 1. Remember 1 is when you're absolutely positive that something will happen. Like I can be 100% sure that the sun is going to rise in the east tomorrow, right? So you're 100% certainty that something will happen, right? So in this case you take that 1 and then you subtract the alpha. And in this case, that's how you get 0.95, which is 95%. And we can say that alpha is 0.05 or 5%. And then you have a relative frequency interpretation. You can say 95% of all the confidence intervals that can be constructed will contain the non-true parameter. So once you do that, you can say, you know, I'm 95% confident that if I build 100 samples of these, 95 of them are going to contain the true parameter, like we saw in a couple of slides earlier. You're not always going to get the true parameter, but it's only going to be 5% of the time that you want. A specific interval either will contain or will not contain the true parameter. No probability involved in a specific interval. So you could be the first interval you do might not contain the true mean of the population. That could happen because there is no probability, right? That it could be the first one or it could be the last one. But it tells you that if you run it 100 times, 5% of the time you're going to be wrong, but 95% of the time you're going to have the true mean of the population in that parameter. Okay, so again, you can build confidence interval for the population mean when you know the standard deviation and when you don't know the standard deviation, and we'll go over that shortly. Or you can do the confidence interval for the population proportion. So let's start with the first one, right? Building a confidence interval for the mean when you know the standard deviation. Population standard deviation, a couple of assumptions we're going to have to do is the population standard deviation is known, so you know the standard deviation. The population is normally distributed, and if the population is not normal, you're going to have to use a larger sample. So you're going to find out that the larger the sample, the more is going to appear to look like a normal population. So you can just use a larger sample. And then here we have the confidence interval estimate. So you have your x bar, which is your mean, and then plus minus c, and then you have alpha divided by 2, and we'll talk about that in the next slide. Why are we using alpha divided by 2? And then you have your standard deviation divided by the square root of the sample size. And this part right over here is what we call, that's what we call the standard error. So the standard deviation divided by the square root of the sample size, it will be the standard error. And then z alpha divided by 2 is the normal distribution critical value of a probability of of alpha divided by 2 in each tail. So this is why we do alpha divided by 2, right? You have your data here, and then you have your tails. So in this case, remember alpha is 0.05 or 5%, and you get 5%, so that means you get 0.025 on each tail in order to get the 0.05. If you use the C table, right, and you can see that this is negative 1.96, and because this is symmetrical, you get the positive 1.96 on the right. but that's where you get alpha divided by 2 because there are two tails. Again, the most common ones is going to be 95. You can do 90, you can do 99. Here are some confidence coefficients, right? So confidence level is 80%. Confidence coefficient will be 0.8, right? 1 minus alpha. In this case, the C value of alpha is 1.28. This is the one that we're going to be using the most, 95% confidence interval. And the Z value, you can memorize this right now, is 1.96. This is the one that we'll use the most. Sometimes if you want to use this one, uh, yeah, those values get pretty high out there. But again, look at this, it's very close to 100%. So again, 100% is useless, 99.9% is also not useless, but you know, it's very wide. So keep that in mind. Here is the sampling distribution, right? You have your mu, so 1 minus alpha, and then you can see the first one contains mu, the second one contains mu, the third one also contains mu, this one also contains mu, this one contains mu, but this one here does not contain the mean of the population. So just keep that in mind that 1 minus alpha is 100% of the interval constructed will contain mu, and then mu will, I'm sorry, alpha 100% do not. So this is where the 5% comes from, or you know, if you're doing 99, 1% or whatever percentage is that you're doing for the confidence interval. All right, let's do a sample to help us do this. So to help us get a grasp of this concept. So this one says a sample of 11 circuits from a large normal population has a mean resistance of 2.2 ohms. We know from past testing that the population standard deviation is 0.35 ohms. In this case, they're asking us to find a 95% confidence interval for the true mean resistance of the population. So a sample of 11 circuits, right? We have that in here. On this case, all we gotta do is substitute, right? So here is our mean. It's gonna be plus minus, and here's our C, which is confidence level that we want, alpha divided by 2. So all we do is substitute here. Here's the mean, 2.20, and then plus minus, here is a level. Remember, in this case, we're doing 0.5 or 5%, and we know already that is 1.96. Right, see it right over here, 1.96. And then you have your standard deviation divided by the square root of your sample size, which in this case is 11. So when you do this 1.96 times this parenthesis here, you get 0.2068. So you get 2.20 minus 0.268, that you get 1.9932. That is your lower level. And then you can say your lower level will equal or be less than your mean for the population, which will be less or equal to 0.2468. So here is the interpretation. On this case, you can say you are 95% confident that the true mean resistance is between 1.9932 and 2.468 ohms. The true mean may not be on this interval, but you are 95% confident. Again, the 5% alpha is because this could be wrong. All right, now let's talk about the confidence interval for population mean when you don't know your standard deviation. And the question is, do you ever really know what the standard deviation is? And the answer is probably not. In mostly all business situations, we're going to have to use statistics. The standard deviations will not be known. If there is a situation when you know the standard deviations, then you already know what mu is, and then you don't need to do this because you say, yeah, you know, the mean for the final score at the college is this, so you already know what it is. Then why would you want to do a confidence interval? If you truly know where mu is, there will be no need to gather a sample to estimate it because you already know what it is, right? So what you do when you don't know the standard deviation, which is going to be most of the time, right? If the population standard deviation is unknown, what you can do is you can take a sample and then you grab the standard deviation for that sample, and then you substitute the population standard deviation. The problem with that is that also introduce an extra uncertainty because now your standard deviation might not be the same standard deviation for the population. As a matter of fact, it will probably change from sample to sample. So what we're going to do is we're going to use the t-distribution instead of the normal distribution. Uh, so couple of assumptions when you're going to build a confidence interval for the mean when you don't know the standard deviation is that one, you don't know the standard deviation, and the population is normally distributed. If the population is not normally distributed, then you're going to have to make sure that you use a large sample, more than 30. On this case, we're going to use the student's t-distribution, and we're going to do the confidence interval estimate. Again, the formula here is pretty much the same as you can see. Instead of the C table, we're going to use the T table, the student's T table, and then you always have the alpha divided by 2. Okay? So the T is a family of distributions, the T table, and then you have the T alpha divided by 2. Value depends on the degrees of freedom. Uh, the degrees of freedom is going to be the number of observations that are free to change after the sample has been calculated. So let's talk a bit more about degrees of freedom. What is this degrees of freedom, right? Suppose that I say, you know what, pick 3 numbers, and those 3 numbers need to have a mean of 3, right? So you can say, okay, I'm gonna pick 7, 8. Now, after you pick 7 and 8, the last number that you pick has to be a specific number. The number cannot change. In this case, this number has to be 9. If you pick any other number besides 9, you will not get a mean of 8. So that's why your degrees of freedom is 2, because the first 2 numbers you can change. You can change the 7 to be, I don't know, let's say 10, right? And then you can change the 8 to be 5. So you have 10 and 5. But in this case, the last number will have to be a fixed number in order to get a mean of 8 for those 3 numbers. So in this case, you have here n equals 3. Degrees of freedom will be n minus 1. So that will be 2. So you have 2 degrees of freedom. That means you can choose 2 values, but the third value will have to be fixed in order to get a mean of 8. Going back to the student's t distribution, you can see that t is going to approach c as the number of samples increases. So again, that's why you say if it's not normally distributed, just take a larger sample, because as you take a larger sample, it's going to appear more to be like a C table. Again, here is the student's T table, right? You have your alpha divided by 2 or 0.05, and then here you have 2 degrees of freedom with the 0.05, and that's how you get the 2.92, which is here. That's the body of the table, contains the values, not probabilities. On this case, remember we have 3 numbers, right? So we have 2 degrees of freedom, which is 3 minus 1. The last number has to be fixed. The alpha is 0.1, which you take on each side as 0.05. And that's how you get that 2.92 for the T table. So the C table and the T table, they're different. Just remember which table you're using for this, right? So here we're just comparing T values to C values, right? You can see at a 95% confidence interval with 10 degrees of freedom, the T table it says 2.28. But as you increase the degrees of freedom or you increase the numbers of sample, this number gets closer to the C table. Here we have a random sample of n equals 25. You have your mean of 50 and your standard deviation of 8. And it's asking us to form a 95% confidence interval for the population mean. So we start with the degrees of freedom, n minus 1, that will be 24. And you have your t alpha divided by 2 of 0.025. And if you go back to the table, right, to your t table, you can see that you will find a value of 2.0639. So here you have your confidence interval. All you do is substitute the values, and you have that 46.698 is going to be less or equal to the population mean, which is going to be equal or less to 53.30. So 46.98 is your confidence interval, and 50 is your lower level, and then 53.302 is the upper level. So interpreting this interval requires the assumption the population you are sampling from is approximately a normally distribution, especially in this case, right, which your sample size is only 25. So you have to assume that it's normally distributed. If not, you will have to get a larger size. This condition can be checked by creating a normal probability plot or a box plot. Um, let's do an example here in Excel so you get so you're familiar with this. So let's do this. Turn to your textbooks on page 285. Let's do this one here. It says an insurance company has a business objective of reducing the amount of time it takes to approve applications for life insurance. The approval process consists of underwriting, which includes a review of the application, a medical information bureau check, possible requests for additional medical information and medical exams, and a policy compilation stage in which the policy pages are generated and sent for delivery. So again, we're using the DCOVA, right? Steps to first discuss on page 3 of the book to define the variables of interest and the total processing time in days. You collect the data, and then here is our data. So let me open Excel here, and what I'm gonna do is I'm just gonna copy those values into Excel. We're gonna do 8, 11, 15, 17, 19, 20, 22, 25, 27, 32, 35, 38, 41, 41, 45, 48, 50, 51, 56, 56, 60, 63, 64, 69, 73, 80, 84, and 91. All right, I got the data here from the problem. So what you're gonna do here in Excel, Excel will do most of the heavy lifting for you. What you're gonna do is you're gonna go to Insert here, and then you're gonna go to Data, and then you need to have the data analysis pack for this. So click on Data Analysis, and then we're gonna do the descriptive statistics. Click OK. So A1 through A27, yes, that's the input range. You want to do your, on this case, let's put our data here. We're going to click here. That's where our data is going to show up. And we want to do a summary statistics at the 95% confidence level. And then we're going to do the confidence level for the mean. You click OK. And here is everything you need to know about this data. Here is your mean. Here is your standard error. Here is your median, mode, all of that stuff. We don't need any of that. But what we really need is the mean. And then we have our confidence level, the 95%. So what we're going to do is we're going to do lower level is going to equals our mean minus our confidence level, and our upper level is going to equals our mean plus what did I do? Our upper level is going to equals our mean plus our confidence level of 95%, and that'll give us the lower level of 36. We're going to run this up to 2 decimals. I'm sorry, rounding on to 2 decimals, right? Okay. All right, so 36.7 and 54.38, and let's go back to our textbook and see what we get here. Here it is, yeah, 36.07 is going to be equal or less than our mu, and our mu is going to be, or our mean, population mean is going to be equal or less to 54.38. So we did get the right value. So this is how you use Excel to find these, to build these confidence intervals. In this case, here is our solution, right? We can say with 95% confidence that the mean processing time for the population of life insurance application is between 36.07 and 54.38 days. The validity of this confidence interval estimate depends on the assumption that the processing time is normally distributed, remember, right? So very important that we assume that it's normally distributed. Okay, what about confidence interval for the population proportion pi? So an interval estimate for the population proportion can be calculated by adding an allowance for uncertainty to the sample proportion. So what do we mean by that, right? We know that the distribution of the sample proportion is proximally normal if the sample size is large enough. And then you have your formula here. This is you have the standard deviation of the proportion is going to equal the square root of pi minus 1 minus pi divided by the sample size, and we estimate that this with the sample data. So here is the proportion, 1 minus the proportion divided by the sample size. So upper and lower confidence limit for the population proportions are calculated using a formula which is very similar to what we've been using. On this case, C alpha divided by 2 is the standard normal value for the level of confidence desired. P is the sample proportion, and N is the sample size. So pretty much the same thing we've been doing. Here is an example. It says a random sample of 100 people shows that 25% are left-handed. And then they're asking us to form a 95% confidence interval for the true proportion of left-handers. So the random sample of 100 people shows that 25% are left-handed. So here is how we construct the confidence interval. You have your population proportion plus minus C alpha divided by 2, and then you have the square root of the proportion times 1 minus the proportion divided by N, which is the sample size. So you got 25 divided by 100 plus minus 1.96, and then you have the square root of 0.25, right, which is your proportion, and then 1 minus the proportion, 1 minus 0.25, then they'll give you 0.75, and on this case your sample size is 100. So then you solve the first part, and then you do plus minus like we've been doing, and that's how you get the 0.651 and the 0.3349. So you can say with 95% confidence that the true percentage of left-handers in the population is going to be between 16.51 and 33.49%. Although the interval from 16.51 to 33.49 may or may not contain the true proportion, 95% of interval formed from the sample size of 100 in this manner will contain the true proportion. So again, we still have some uncertainty there, the 5%, right, where it might not be there, but in general, that's how you will do it. Okay, we're gonna finish this talking about determining the sample size, right, for the mean and for the proportion. So sampling error. The required sample size can be found to reach a desired margin of error, which is a specific level of confidence, which is 1 minus alpha. The margin of error is also called sampling error, which is the amount of imprecision of the estimate of the population parameter, right? That's where you have the lower, the upper level, because there is some uncertainty. You don't know exactly what it is. You can tell, 95% of the time it's going to be there, but there is some uncertainty. You don't know what it is, right? So the amount added and subtracted to their point of estimate to form the confidence interval. So how do you determine the sample size? How do you know you need 100 people, like on the prior example, but you need 100 people to get a good confidence interval, right? So for the mean, you have the formula, and here is your sample size, and all you have to do is, and here is your sampling error, right? You take a look at this. It is the same thing right here. Is the error is going to be the z of alpha divided by 2, the standard deviation divided by the square root of the sample size. So what you do is you solve for n, and that's how you can find out what the right side, what the correct sample size is. So you select for you solve for n. So to determine the required sample size for the mean, you need to know the desired level of confidence. Obviously, you're going to know whether you want to be a 99, 95, 80. Okay, so that will give you your critical values, which is C alpha divided by 2. And then you have the acceptable sampling error. You need to know that, what your acceptable sampling error. And finally, you are going to need your standard deviation. So if you need those three, you can calculate what the sample size that you need uh, for this, right? So here's an example. So you have a standard deviation of 45, and the question is what sample size is needed to estimate the mean between plus minus 5 with 90% confidence. So going back to your formula, you know that the n, or the sample needed, is going to be c squared, standard deviation square, error square. So in this case, because we're doing 90%, the c of is going to be 1.645 square, and then the standard deviation is 45. You square that one, and then you want plus minus 5, right? So that is your error. So that you square that one and you get 219. Now remember, you cannot run, you have to run even numbers, right? So in this case, you run up 220. If you were to run 219, you will be short. So you need a sample size of 220. If this was 2.19.01, you will still need 220, because you always round up. If you do 219, even if it was 0.1, you are not going to have enough sample size. So if the standard deviation is unknown, like in most cases will be, you can also estimate when using the required sample size formula. What you're going to do is you're going to use a value for the standard deviation that is expected to be at least as large as the true standard deviation, and then you select a pilot sample of estimates standard deviation with the sample standard deviation. So let's take a look at see what that looks like here. Here is you for the proportion. See the formula, you have C, and then you have the square root of pi 1 minus pi divided by the sample size, and then again you solve for n, and it's going to be pretty much the same process. So to determine the required sample size for the proportion, you must know the desired level of confidence, right? You gotta know what confidence is, which determine the critical value. You have the acceptable sampling error, and you need to know the true proportion of events of interest. P. So P can be estimated with a pilot sample if necessary, or you can use 0.5 and estimate for P. So how large a sample will be necessary to estimate the true proportion for several invoices containing errors in a large population between plus minus 7% with 95% confidence? In this case, you're going to assume a pilot sample yields P of 0.15. So let's work on that one. Here's our solution. So for 95% confidence, you're going to use Z alpha divided by 2. Remember 95, 1.96. And in this error is given to us by the example, the acceptable errors, this 7% here. That's what this 0.07 is. And then you have your P of 0.15. Again, this is we're going to assume a pilot sample yields the population proportion of 0.15. And then all you gotta do is just substitute those values, 1.96 squared times 0.15 times 1 minus 0.15 divided by 0.03 squared, and then you get 99.96. On this case, always you round up, and that's how you get that 100. Couple of things you need to keep in mind when reporting data, right? Make sure that you use a confidence interval estimate reflecting sampling errors. So you should always be included when reporting a point estimate. You should also tell them the level of confidence that also should be reported. So you know what, I'm 90% confident that the true mean is going to be here. And finally, an interpretation of the confidence interval estimate should also be provided. Okay, so on this chapter, we talk about constructing and interpreting confidence intervals estimates for the mean and the proportion. And we also talk about the sample size, what sample size, how large, how small it should be in order to build a confidence interval for the mean, for the proportion. And this is the end of the chapter. And this pretty much is the end of the semester. We still have the final exam. So reach out if you have the questions. I'm here to help. Send me a message in Canvas. That is the best way to reach me. If something doesn't make sense, if I just jumble here and it's hard to understand and I put you to sleep, do not hesitate to reach out to me and see what best I can do to help you. All right, looking forward to hear from you guys. I know we can finish the semester strong. I know you have been working really hard for the last 7 weeks, but we can do this. Let's finish it.